Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. You may have heard of perovskites, a class of materials defined by a particular crystal structure. Researchers are currently developing perovskites for the next generation of solar panels. The perovskites can make for much more energy-efficient solar cells, as Barry Rand, a materials scientist at Princeton University, explains.
You can put a perovskite cell atop a silicon cell in a so-called tandem or multi-junction arrangement, and this has the capability of making an even better device than either silicon or perovskite could hope to be on their own.
However, experts still don't understand some of the basic science behind perovskites. To use them in electronics, they need to better understand, for example, how perovskites interact with metals. In new research, Rand and his PhD student Tuo Hu studied how a perovskite interacted with gold. Hu explains.
We wanted to understand how the movement or the reactions of gold and perovskite can influence the property of the perovskite itself.
Specifically, they studied a device made of the perovskite methyl ammonium lead triiodide bonded to a gold electrode and an indium tin oxide electrode. Indium tin oxide is a transparent conductor, also known as ITO, that is commonly used in solar cells.
This is a three-layer structure, starting from the indium tin oxide, and then we deposit the perovskite, and then the gold electrode.
It's like a sandwich with 100 nanometers of gold on one side, 100 nanometers of ITO with the perovskite in the middle. The whole sample is about 1/10 of a square centimeter. They applied a constant voltage to the device. Because of this applied voltage, the gold electrode gives up electrons to the perovskite to become oxidized. After applying the voltage for up to 2 hours, they removed the gold electrode with tape and washed off the perovskite layer with organic solvent to expose the underlying ITO interface.
We started to see there are a lot of bright particles, so like some islands, uniformly distributed on the ITO substrate. The oxidized gold species can migrate from the gold interface all the way to the bottom interface between ITO and perovskite. So it traversed an entire perovskite bulk.
They imaged the device using scanning electron microscopy and X-ray photon electron spectroscopy to visualize and quantify the amount of gold deposited on the ITO interface. They also studied the speed at which the gold went through the perovskite.
If you're under a bias of like around 1.1 volt, then gold can migrate through this 200 nanometers of perovskite within 14 seconds.
They also found that they could reverse the process by reversing the voltage.
We can send gold one way and then actually strip it and send it back. This is probably the most surprising results.
This reversibility reminded them of solid-state batteries, where ions travel through the entire bulk of the solid-state electrolyte, but without an applied voltage.
It's similar to electroplating of lithium ions in both solid-state batteries as well. So we can draw some really cool analogies between the perovskite system that we're studying to the well-known solid-state batteries field.
The charges in their device move 2 to 3 orders of magnitude slower than charges in a solid-state electrolyte battery. Still, they think that drawing parallels between perovskites and solid-state batteries could be very powerful, as lessons from solid-state battery development could apply to perovskites. Their study also could help the community reframe how to think about ion defects in perovskites.
We shouldn't frame ion density as a constant. This thing is very much a function of bias, a function of your stressing condition, whether you have light around. I think a lot of the halide perovskite community likes to think about ion density as some constant value, but it's definitely not. It's definitely something that is changing in time and space as you are stressing this device.
In addition, they point out that this device could be useful for a type of technology known as a memristor. Memristors store information in materials whose resistance can change. When the material is at one resistance, that could correspond to a 0, while another resistive state corresponds to a 1. In their device, they can reduce the resistance by injecting the material with gold ions. They can increase the resistance of the device by reversing the flow of gold ions. Thus, the device can switch between 2 resistive states. This work was published in a recent issue of Energy and Environmental Science. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X. at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.